Good morning, all. Am I audible? Guys, can you hear me? Shall we start this session? Okay, fine. I hope there will be no issues. Let us start this session. So, in the last class, we have been discussed about basics of power electronics, like when we have a diode circuit, how diode will be basically behaving when we are connecting a diode circuit with the DC. So input we given as a DC, and the output side we have observed its correspondent behavior. Just we have gone through it, we have revised. I know that because it is a training session here. It is not possible to give proof for everything. You can understand these operations in our lecture. So what we understood, when we are connecting different types of loads with the DC supply through diodes, we understood how they are performing. Now it's time to do the start the rectification process. What we are going to do. So rectification process means, suppose if I am taking a diode, not only a single diode, we are going to increase the diode count continuously. When I am connecting a single diode with an AC supply, AC means we know alternating quantity. And the output side, as usual, we are going to connect variety of loads. You can connect R load, you can connect RL load as usual. You can connect RC load also if you want, you can try. And you can connect RLE load, RE load and RLE load. What is the difference? This is a kind of battery. Here we are ignoring the effect of inductor. RLE load means we will be considering RLE load. So basically these are the types of the load that we are considering in the output side. We will be connecting R load, we will be connecting RL load, we will be connecting RC load, we will be connecting RE load, we will be connecting RLE load. That's all. So when we are connecting this kind of different loads at the output side, how this diode is basically doing the rectification process. First of all, what we have to understand here is we need pure DC in the output side, but that is not possible as of now. We are just doing the rectification converting process. After that, some filtering action is required at the output terminal. That part is separate. Here we are not going to deals about that. So we are going to simply connect. Suppose let us see what will happen when we are connecting the diode directly. One terminal of the diode will going to be connected with the load, and another terminal of the diode will be going to be connected with the supply, and a return path will be interconnected like this. Now what will happen? How this rectification process will be happening? How we are basically converting the AC supply into DC supply? That is called rectification process. Now kindly go through these operations at all in our lectures, right? So here that is not possible to recapture everything, but I will be covering the important parameters that you must keep it in your mind. Some things are mandatory. I will be covering those things. Fine. Chalo. Now, suppose I'm taking, diode can be broken into two of. One is called single phase right? Single phase diode rectifiers. We are going to consider single phase diode rectifier, and we will also going to consider three phase diode rectifier. Three phase diode rectifier. So let me write everything one by one here. So in single phase diode rectifier, first we are going to write the expression for average output voltage, V0 average. That is very important. So when we are considering single phase diode rectifier, once again it will be broken into half wave rectifier and a full wave rectifier. Similarly, if you consider three phase, in three phase also once again it will be treated as half wave rectifier, three phase, half wave rectifier, and again we are going to consider full wave rectifier. Now V naught average will be placed somewhere. Wait. So here if you take this half wave rectifier, sorry, full wave rectifier, this full wave rectifier again broadly classified into two types. What are those? Again, if you consider here also, this full wave rectifier will be broadly classified into two types. Not two types, basically based on the construction. We know while designing the half wave rectifier, the one perception we can design the full wave rectifier with the help of bridges. We can also design this half wave rectifier with the help of midpoint center tapping. So that is called midpoint center tapping. There are two types. Here also we can consider the same thing. One is midpoint center tapping and another one is simply we can write bridge rectifier. So basically there are two types. Now let me write the expression for all these people. We are taking first, we are going to consider half wave rectifier, then mid wave, then bridge rectifier. Again we will be considering half wave in three phase, then mid wave, then bridge rectifier. So it is very important to know these parameters because in the examination the most repeated area, 80% of the question will be asked based on average output voltage, V naught average. Now, anyone can you tell me what is the V naught average output formula for if you are considering a single phase of a rectifier, diode rectifier? I'm talking about diodes, not thyristor. So basically it will be simply coming up maximum voltage divided by pi. First conclusion. If you consider midpoint center tape, it will be automatically become 2 times of Vm by pi. That is twice of half wave. If you consider bridge rectifier, you all know there will be no changes in the output voltage. In both cases, you will be coming up with the same 2 Vm by pi. Okay, sir. Suppose if you consider three phase, so here what will happen is you will be coming up with the 3 times of maximum line voltage divided by, we have to divide it by 2 pi. So this is the V naught average for three phase of your rectifier, but construction is diode. Don't forget, that is very important. Suppose if we are talking about 6 pulse midpoint and C. One more thing I would like to, this full wave rectifier when I considering, first let us take midpoint and a bridge. While going up with these three, if we talk about three phase half wave rectifier, we will be calling about 3 pulse. How many pulses are there in the output? 3 pulse. If we take midpoint, in midpoint basically we will be having 6 pulse. I'm just denoting it by. But in bridge rectifier there are two cases. Either we can bring 6 pulse, we can also bring 12 pulse. Okay, let us do one thing. I will be writing both the 6 pulse and the 12 pulse. Okay, it will be helpful for you. First, let us write for midpoint 6 pulse rectifier. That is full wave. No? If you write like this, here you will be coming up with 3 times of maximum voltage divided by, see, it is just a maximum phase voltage. We can write 3 times of maximum phase voltage divided by pi. We can simply write, or we can also write in terms of line voltage. We know basically it is star connected. Midpoint means we will be connecting star connected loads with this. So we know in case of when the load is star connection, then line voltage equal to root 3 times of phase voltage. If you want to replace the phase voltage by line voltage, then phase voltage will be replaced by line voltage upon square root of 3. So if you are writing like this, so 3 into this maximum phase voltage can be written as maximum line voltage upon square root of 3. So I'm just converting this value from phase to line divided by pi. Now you all know 3 can be rewritten as root 3 into root 3. So 1 root 3 will be cancelling out. Finally, this value can be written as root 3 times of maximum line voltage upon pi. So this is the formula for what? Full wave 3 phase diode bridge rectifier. Okay, but this is midpoint, don't forget. Now let us keep our attention to the bridge. In bridge, basically first we will be focusing on 6 pulse. So basically what is this number of pulses? Output la 360 degree kulla ungalku output la ethana pulse varudho, that is called a number of pulse. See, let me tell you. Suppose I am drawing the waveform for the output. If the output is producing only two pulse, sorry, single pulse means only one pulse will be appearing in 360-degree. If you observe from 0 to 360, you will be observing only one pulse. Suppose in between 0 to 360, if we are observing two pulses like this, then that is called a two pulse converter. No, sir, I am observing between 360-degree, I am observing three pulse. 1, 2, 3. No, sir, I am observing 6. 1, 2, 3, 4, 5, 6. No, sir, I am observing 12. But it should be between less than, sorry, it should be exactly till 360-degree only. From 0 to 360-degree, how many pulses that we are observing in the output? Whereas in the input side, we are giving only single sinusoidal waveform. But in the output side, we are trying to convert it into 3 pulse, 6 pulse, 12 pulse, 2 pulse, 1 pulse. Based on this only, it will be categorized. In case if you consider the half wave rectifier, you will be receiving only 1 pulse. In case of full wave rectifier, that is full wave means I am talking about single phase. Single phase half wave rectifier 1 pulse. Single phase full bridge rectifier 2 pulse. 3 phase half wave rectifier 3 pulse. 3 phase full wave rectifier 2 cases. One is 6 pulse, another one is 12 pulse. So this is how we are identifying the number of pulses. Okay. Fine, sir. Now come back to the bridge rectifier, but it will be having 6 pulses. When it is having 6 pulses, then the formula can be simply written as 3 times of maximum line voltage by pi. Okay, fine, sir. Then what can be the answer for 12 pulse? So I'm writing here itself bridge rectifier only, but it is 12 pulse. 12 pulse means we can simply write it will be 1.91 times of maximum line voltage. 1.91 times of, see, there is basically by using calculator I have done this calculation. So it is 1.91 times of maximum line voltage. So these are all the formula that you must remember when you are focusing on diode voltages. That is very important. Okay, now next people what will be asking often in the examination is peak inverse voltage. So basically, what is this peak inverse voltage? Let us talk about peak inverse voltage for the same people. When we are taking peak inverse voltage means maximum voltage blocked by the diode. Maximum voltage blocked by the diode. Where it will be blocked? See, blocked by diode means suppose we will be passing some sinusoidal signal from the input side, and in between we have the diode circuit. In the output side, I am observing only one pulse is there. I don't know where is that second pulse. In between, see, input is your source. So what I can say is supply voltage will be always equal to voltage drop across the diode plus voltage drop across the output load. So now supply voltage, from the supply I have been passed a complete cycle. Only one cycle is appearing in the output side. It indicates automatically another upside will be blocked by the diode, or it will be simply dropped across the diode. So definitely we can draw like this. So the another half of the voltage will be dropped across the diode. Voltage, this for diode will always be blocking reverse voltages. So when the diode is blocking the reverse voltage, what is the maximum negative voltage that can be blocked by the diode? That is called peak inverse voltage. See, peak means maximum voltage, inverse means negative voltage. So maximum negative voltage blocked by the diode. In the name itself, I am representing negative. So while writing the expression, you no need to put the minus in front of the expression. Like peak inverse voltage means you no need to write like this, sir, minus V max. It is not required. This minus is not required. Why? Because name itself, I know that name itself, I'm suggesting that peak negative voltage, negative peak inverse. That is called peak inverse voltage. So basically, peak inverse voltage means maximum negative voltage blocked by the diode in the circuit. Okay, so that is the most important question. Once again, let us take single phase half wave rectifier, single phase full wave rectifier. So there are two people. One is midpoint, another one is bridge rectifier. Similarly, if we take full wave, three phase half wave rectifier, three phase full wave rectifier, one is midpoint, another one is bridge rectifier. So in bridge rectifier, as usual, we will be having 6 pulse, another one is 12 pulse. Let us start our operation. I will be writing peak inverse voltage somewhere here. Guys, I cannot bring everything here. I have already told you. Remaining things must be you taken care by you people. Okay. Okay, sir. So if you take half wave rectifier, what is the maximum peak inverse voltage that can be blocked by the half wave rectifier? Any one of you having any basic idea for this? So the maximum voltage blocked by the half wave rectifier is maximum, just simply Vmax. If you observe full wave rectifier, that to midpoint will be dropping twice of the maximum voltage. Most important point. Supply வந்து இப்போ நீங்கள் maximum voltage வந்து 400 root 2 அப்படின்னு கொடுக்குறீங்கன்னா it will be what will happen, it will be 800 times of root 2 மாறும். So it will be doubled here. Okay, that is the drawback of peak inverse, sorry, midpoint bridge rectifier, sorry, midpoint full wave rectifier. If you take bridge rectifier, as usual it will be blocking only maximum voltage. Similarly, if you observe 3 pulse half wave rectifier, that is half wave rectifier means 3 pulse only. So it will be backing only maximum line voltage simply. If you go ahead with the 6 pulse, that is midpoint rectifier 6 pulse. So it will be blocking 1.155 times of maximum line voltage. One point is there, 1.155 maximum line voltage. A 6 pulse rectifier, it will be blocking only maximum line voltage. If you take 12 pulse, there will be no such concept. All diode will be in conduction always. So 360-degree diode will be in conduction. So total voltage will be simply appearing across the output. Okay, there is no such type of word for the 12 poles bridge rectifier. Okay, fine, sir. So this is the peak inverse voltage for values for all the diodes properties. That is the most important formula that you must remember. Next, the repeated question in the examination is, what is the ripple frequency? What is this ripple frequency, sir? Ripple frequency means how many pulses that we are receiving. Based on that, your frequency will be decided. See, ripple frequency means what is the relation between input frequency and output frequency. Output frequency equal to n number of times of input frequency. That's all. Now here, this is the output frequency is simply called ripple frequency. Both are same only. Ripple denotes the number of pulses. Here I am indicating the number of pulses by n. Now if you take single phase half wave rectifier, how many pulses you are having? Only one pulse. So we can write output frequency will be equal to n equal to 1. So 1 times of input frequency. So both are same only. If we take a full wave rectifier, but it is what? Diode single phase full wave rectifier. How many pulses are there? 1, 2. So in that case n equal to 2. So output frequency equal to 2 times of input frequency. Output equal to simply ripple frequency. Don't forget, both are same only. Single phase half wave rectifier, if we take output frequency equal to what will you keep here? As usual, you have to keep 3 times. So ripple frequency here it is going to be 3 times. So I can write 3 times of input frequency. Now how will you write out the ripple frequency for 6 pulse? It will be 6 times of input frequency. 12 pulse means it will be 12 times of input frequency. So that is how we are identifying the number of pulses. So ripple frequency can be written as, here it is only one ripple is there. It will be 2, it will be 2, it will be 3, it will be 6, it will be, sorry, yes, it is 6, it is 6, it will be 12. Yes or no? 6 times of ripple frequency means 1 times of input, 2 times of input, 2 times of input, 3 times of input, 6 times of input, 6 times of input, 12 times of input. So this is how we are writing the ripple frequency for all other people. That is the most important term that you must remember. Okay, sir. So the next most question that will be repeatedly asked in the examination is, what is the output RMS voltage? Output RMS voltage. Now, if you keep your attention with the half wave rectifier as usual, the output RMS voltage will become Vm by 2, not Vm by root 2. It's not like general expression. It will be derived based on the output expression. Sir, you might be keeping one more thing in your mind. Sir, why are you not considering any type of load here? Like resistor load is there, RL load is there, RE load is there. Without considering those loads, how we are writing this? See, this is called general expression. In your examination, if you observe, most of the questions will get repeated without considering the loads. People are assuming that the output is having continuous conduction. So when we are looking for discontinuous conduction, in that case, it is very important to consider the types of the loads. Continuous conduction means we are assuming that the inductor that is connected in the output side is very large. That property, it is having very large value, and it is producing its property is sufficient to produce the continuous conduction. Without having any discontinuity, we are observing the continuous conduction. Basically, we will be having two types of conduction at the output side. One is called continuous conduction and another one is called discontinuous conduction. So we will be assuming that we are having only continuous conduction. Based on the continuous conduction, what can be the generalized observe the output voltage and RMS, output average voltage, RMS voltage, ripple and frequency, everything. So these kind of general questions you can observe often in your examination. They won't be talk about the type of the loads. Simply you will be requested to observe the nature of the voltage, output voltage. In that case, you are requested to use these formulas. And it is also important to know the output average voltages load wise. If I will connect R load, what will happen? If I connect RL load, what will happen? See, in our lecture, if you observe the complete operation of rectifiers, that is thyristor based lectures, if you complete all those things, it will be automatically help you to derive the to draw the output waveforms for the diode circuits. You can take a diode circuit, simply do the operation by yourself, because power electronics is not a big thing that you have to study from any all by using multiple resources. If you understand the basic operation of any one switch through the with the help of notes or video lectures, it will be helpful for you. If you understand it properly, then automatically you can draw the waveform for any type of circuit by yourself. Okay, sir. So V naught RMS for half-wave rectifier single phase is Vm by 2. If we take mid wave, it will be Vm by root 2. And the next one is, I think this is also Vm by root 2 only. There will be no changes in the RMS voltage. So if you observe, in case of half-wave rectifier, I think it will be 0.48. 0.48 times of maximum line voltage. 0.485 times of maximum line voltage. And this I know it will be 0.5518 times of maximum line voltage. And this one will be for 6 pulse I'm writing 0.99, I think. Wait, it will be 0.9558 times of maximum line voltage. See how to memorize all these things. Some cases need to be required, how to memorize, because it will be reducing your time in the examination. Sir, why should I memorize? I can know, I know how to derive. In that case, you can do, but it is unnecessarily wasting your time. Power electronics, it is very important to remember something in your mind such that you can save your time directly in the examination. You can directly type your answer if you are remembering all these expressions. That's why I'm giving these things. Otherwise, I would have asked you to derive it by yourself. Nothing is there. Okay. Are you guys are sleeping? No. Just keep smile in your face. I know lecture is a little bit boring because we haven't started problems yet, right? Fine. So what I'm requesting you is, apart from that, there are some things that you have to observe, like how to write down the output voltage expression for single phase of a diode rectifier when we are connecting with a simple diode. If we take only half wave rectifier, if I'm connecting only diode, and input is AC supply single diode, and output is, if you connect R load, what can be the output voltage. So here it is very important to know the average output voltage V naught. Just now we have derived, this is common only. Same, if you connect R load, you will be coming up with the same Vm by pi. This is V naught average value when you connect the R load. Okay, sir. Then what can be the RMS voltage for R load? V naught RMS also will become simply Vm by 2 only. There will be no doubt. It will not be root 2. Remember one more thing. Okay, and it is very important to know how to calculate the input power factor. I would have requested you to do that. If you know peak inverse voltage will be equal to Vmax. Okay, at the same time, you should learn how to calculate the input power factor, IPF. This is called input power factor. So what is the basic formula? Basically, you might have observed this. IPF, input power factor formula, is how much amount of power delivered to the load. That is, simply we can say power consumed by the output power, divided by, we can put input power, but it should be in kVA rating. So now it is time to explore these things. If you take the RL load, so in the output power, what you must consider is, basically in both sides you are requested to consider the RMS voltage, RMS powers, RMS voltage, RMS current. So how will you write? Output power we can write V naught RMS into I naught RMS. Simply we can write. Input power we can write V input RMS and V input, I input RMS, I input RMS voltage, RMS current. So now you have to substitute all the values. So what is the value of V naught RMS? It is here. From this you can calculate I naught RMS. How will you calculate the I naught RMS? I naught RMS equal to V naught RMS divided by R. V naught RMS divided by R. And here in this circuit, I naught RMS and V naught RMS both see. Output RMS current, input RMS current, both will be same here. Both are connected in series. Whatever the current that is going here, same current will be coming here. So it will get cancelled. And if you observe, output RMS can be simply written as Vm by 2. But if you observe the input RMS, input RMS, how will you write it? It will be simply Vmax by root 2. That is the difference. Why it is? Because input is simply sinusoidal supply voltage, whereas in the output voltage you will be receiving only one pulse. That is the difference between these two. Vmax will be cancelled. This 1 by 2 will be appear here. This 1 by root 2 will be appear in the numerator. Once again, 2 can be written as root 2 into root 2. 1 root 2 will be cancelled. 1 by root 2 can be written as 0.707. So this is how we are estimating the value of input power factor. So you must learn this, how to calculate this input power factor for all other circuit. When we are connecting the RL load and all other different loads, how should I calculate this input power factor? Okay, it is your responsibility to learn these things, because this is also one of the most important parameter which will be asked often in the examination. Okay, sir. So try to calculate these the same parameters for all other different types of load. If I'm connecting, okay sir, if you are connecting only diode, okay, then this can be the formula we can simply write. If you are connecting some all other diodes, then how do I calculate this? Okay sir, fine, that is your responsibility to do. Then I have asked you to understand all these things and how to calculate these formulas, and I have requested you to calculate the harmonic factor. What is the formula to calculate the harmonic factor? Anyone express this? Harmonic current divided by fundamental source current. We can write like this. Harmonic factor. Harmonic current can be written as square root of total source current delivered by the source minus fundamental source current delivered by the source whole divided by, it will not be under root, it will be out of root, fundamental source current. Okay, this is the formula to express this. Similarly, because see, source current அப்படினா source வந்து வெறும் purely fundamental current மட்டும் express பண்ணாது. It will be expressing fundamental plus harmonic current. Harmonic means all other. It can be a DC component, or it can be third harmonic, fifth harmonic effect, seventh harmonic effect, second harmonic effect, fourth harmonic effect, whatever it is. All the current will be merged here. So this harmonic current simply, it can be expressed as, we can consider all other component. It may be a DC component, or it may be a third harmonic effect, or it may be a second order harmonic effect. So all the current will be considered as harmonic only here. So that will be simply written as IH square. This is the general formula to express the value of harmonic factor. Okay, similarly, you will be requested to calculate the ripple voltage. How will you calculate the ripple voltage? What is the formula to calculate the ripple voltage? Same. If you want to calculate the ripple voltage, you must be keep your attention with the output. So what you have to do is just to take the output RMS voltage minus output voltage. Just to find the difference between these two, it will give you the value of ripple voltage. Then how do I calculate the voltage ripple factor? I asked you to learn these things. Yes, voltage ripple factor is nothing but the ratio between ripple voltage and output voltage as usual, total output voltage. So how do I write this? Square root of V naught square, that is V naught RMS square minus V naught square. Without root you can keep output voltage here. This is the formula to estimate the value of output voltage ripple factor. Guys, here I'm repeating once again, it is not time to derive everything. So I have given sufficient things that are required when we are considering only diode. Now it is your responsibility to explore remaining all other activities. How do I calculate all these things? Okay, spend some time. I told you, must spend some time to learn these things because it is important. So it is important to learn these things by yourself. If you learn this by yourself, then only it will be registered into your mind. Okay. Fine. So now, so far we have been discussed about uncontrolled rectifier circuit. Uncontrolled means what? Uncontrolled means if we take a diode, can you control the diode? Like, இப்போ நம்ம SCR எடுத்துக்கிட்டோம் அப்படின்னா, with the help of the gate, I can control. You can say if gate current is 0, what will happen? If gate current is injected, what will happen? So SCR, though it is having anode and cathode terminal, though we are connecting positive voltage, negative voltage across these two terminals, though we are trying to inject the current, all these parameters, whether the SCR will be turn on or turn off, that things will be decided by the gate current only. For how long we must inject the gate current in order to turn on the SCR. Yes or no? These kind of operations will not be there in the diode. Basically, what will happen is if you inject the positive voltage across the anode, negative voltage across the cathode, diode will be turned on. So we cannot control this. If you are injecting positive voltage, it will turn on. If you are injecting negative voltage, it will be turn off, open circuit. But we can't control this with the help of another gate terminal. So this is basically called uncontrolled switch. So with the help of this uncontrolled switch only, we have done our operation so far. But quite what we understood is we are unable to control this diode property. Because of this, there will be no any rectification process in the output side. People understood that we can't do anything. Simply if you connect a diode, you can whatever the things that you are receiving in the output side, you can simply take. You can't do anything apart from that when we are having the diode. That is what people understood. ஓகே சார், அப்போ டயோடு மட்டும் வச்சுக்கிட்டு நம்மளால என்ன பண்ண முடியாது அப்படின்னா, நமக்கு தேவையான things on the output receive பண்ண முடியல. So what we have started is people started thinking about it. They have invented one more thing that is called thyristor. So with the help of the thyristor, we can control the output voltage, output current. We can receive only the parameters that we want in the output side by changing the effective things, by giving the gate pulse, that is called alpha, by giving the gate pulse at the right time. If you are defining the time in terms of degree, that is called angle. Degree can also be considered as angle. So now what is the thing is, in case of thyristor, we have to decide. First we have to inject the positive voltage across the anode and negative voltage across the cathode. Next, this turn on process of the diode is depends on the gate. At which time we are going to inject this gate current. That's time will be defined in terms of angle. That angle is simply called firing angle. Like இப்போ நம்ம கன் எடுத்துட்டு ஃபயர் பண்ணுவோம்ல, அந்த மாதிரி ஃபயர் பண்ணுவாங்கல்ல. ஸோ அந்த மாதிரி என்ன பண்ணுவோம் அப்படின்னா, எஸ்சிஆரை வந்து டக்குன்னு வந்து நம்ம என்ன பண்ணுவோம் அப்படின்னா, டர்ன் ஆன் பண்ணுறதுக்கு கேட் கரண்ட் வந்து இன்ஜெக்ட் பண்ணுவோம். அந்த இன்ஜெக்ட் பண்ணுற ஆங்கிள் ஃபயர்டு, தட் இஸ் கால்டு ஃபயரிங் ஆங்கிள். So you'll be observing that often in the examination, sorry, in your textbook at all. Alpha, standardly we are using it for representing the firing angle. So firing angle means it is the angle in which we are trying to turn on the SCR in terms of gate current. Okay, that is called controlled switches. So basically we people are calling it as phase controlled rectifiers. So the next focus we are going to keep is phase controlled rectifier. Phase controlled rectifier. Guys, I have also covered remaining all other parameters that are required in the examination point of view. It is available in our short notes. Here I can't cover everything, I am repeating again. So kindly go through the short notes, that will be helpful for you. You can easily go through, it won't take much time. So spend some time to understand everything properly, then apply it while solving the problem. Automatically you'll be able to solve all the things. Okay. So don't be bothered about it. If you have, see, while solving the problem, if you find anything new, just to make a hint of it, that's all. Okay, now tell me, when we are connecting same, நம்ம என்ன பண்ண போறோம்னா, first let us take one single SCR, ஒரே ஒரு SCR மட்டும் எடுத்துக்கிட்டா, input side I am going to connect the AC supply, in the output I am going to connect only simply R load. Under this situation, this is simply called single phase half wave rectifier. We people are calling it a single phase half wave rectifier. So when we are connecting a pure resistive load with the single phase half wave rectifier, what can be the expected average output voltage? Can you please tell me? So the value of V naught average will become simply what? Vm by 2 pi into 1 plus cosine of alpha. Alpha is the firing angle. We know that. Yes, sir. Similarly, here I am writing RMS voltage is important for this R load of rectifier R load. So here I am giving the RMS voltage. This is Vm by 2 into square root of pi into 1 minute. I have to open the bracket. So here it will be pi minus alpha plus sine of 2 times of alpha whole divided by 2. We must keep all this under square root. So this is V naught RMS formula. Now suppose at some times you will be requested to calculate the RMS output current or average output current. If you want to RMS output current, what is the output load here? R. According to Ohm's law, we can simply say RMS output current equal to RMS output voltage divided by R. Where is RMS output voltage? It is here. Substitute here, you will coming up with this answer. Similarly, if you will be requested to calculate the value of I naught average, how will you do that? That will be equal to V naught average, average output voltage divided by R. So we know the value of average output voltage. Just to substitute this value here, divided by R, you will be coming up with the average output current. Okay. Okay, sir. Fine. Next, how do I explore the input power factor, IPF? We know the formula. We should do. We have to identify the total power consumed by the load in the output side. But here we are considering only RMS parameter. Don't forget that. As usual, input kVA rating, right? It will be in apparent power. So apparent power, here also we must consider RMS parameters. So it is time to explore. If you do like that, as usual, what you will get? V naught RMS into I naught RMS divided by V input RMS I input RMS. But these two people cancel here once again because it is resistive load. It is directly connected in series with our all other parameter. So output RMS current and input RMS current both will be equal. We can simply write output RMS voltage divided by input RMS voltage. So now you can directly substitute that. As usual, input RMS voltage will become Vmax by root 2. Output RMS voltage we know just now we have written here. You can substitute this expression here. You will get the input power factor formula. I am repeating, input RMS voltage simply Vmax by root 2 only. There will be no changes. Output RMS just now we have explored. Substitute that value, you will be getting input power factor formula. The next most important term when we are discussing about thyristor is circuit turn off time. Most repeated area. Circuit turn off time. So basically it will be represented by TC. What is the formula to explore this value? In case of half-wave rectifier, it will be omega TC equal to pi, I hope. So from the circuit turn off time will become pi by omega. Omega will be directly given in your examination. You will be asked to calculate the circuit turn off time for half-wave rectifier with the R load. With the R load means you have to use this formula. Okay. Yes, sir. I hope you all will be understanding this. Okay, sir. This is the important parameter that you must keep in your mind when we are going up with the R load. No, I am taking the same SCR, that will be undoubtful. But now I am going to connect resistor plus inductor. So this is simply called RL load. Again, I am going to connect it with the AC supply. Under this situation, what can be the expected and observed output voltage? Keep smile in your face, don't be sleep. I hope you won't sleep. because we are not solving problem. Just today we will be completing this because that is very important. Some of you might not observe these things. Vm by 2 pi formula is what? Cos of alpha minus cos of beta. So this is the formula to explore the value of V naught average output voltage. Okay, sir. Now you can also explore the value of V naught RMS. Guys, here I am bringing only important parameter. I am repeating. I am not going to write all the expression for all the people. Remaining things you can observe in our notes. Okay. So Vm by, as usual, it will be 2 into root of pi. There will be no doubt, under square root. Here it will be coming up with the beta minus alpha, minus here it will be 1 by 2 times of, in bracket it will be sine of 2 times of beta minus sine of 2 times of alpha. Now we can close the bracket and keep them under root. Okay, sir. Next, what is the formula to estimate the value of circuit turn off time TC? So here it is 360 degree minus beta upon omega. Most important repeated question in the examination. Do remember the circuit turn off time for RL load with the thyristor of a rectifier. This is very important. And there will be one more question often will be asked in your examination, that is gamma. Gamma means what? For how many angle, for how much angle diode will be in conduction. So this is the conduction angle of diode. If you want to know the conduction angle of the diode, just subtract beta minus alpha, because beta is the point where diode will going to turn off. Alpha is the point where, not diode, sorry, this is thyristor, conduction angle of thyristor, forgive me. Okay. So beta is the point in which at which thyristor will going to turn off. Alpha is the point it will going to turn on. So if you subtract these two, automatically it will give you the conduction angle of the thyristor. Okay, fine, sir. Now it's suppose if I am taking this RL load with the freewheeling diode. See, this is without freewheeling diode. One more thing, I hope all of you know about this freewheeling diode. No issue. If you don't know, just to go through our lecture, there you'll be observing. I will be talking about this freewheeling diode often. Okay, fine, sir. Now I am taking same circuit, same RL load also, no doubt. But this time I'm going to connect this circuit with the what? Freewheeling diode. With the freewheeling diode, you can write the second expression as usual. Input is alternating cycle. So if you connect your circuit with the freewheeling diode, basically the what will happen in the output voltage? Let me write. So the changes V naught average can be written as usual Vm by 2 pi. Observe the output 1 plus cos alpha. It is same as your R load. Yes, of course, that is true only. When we are connecting the freewheeling diode, it will be behaving like this. Okay, sir. Next, as usual, what is the formula to estimate the value of V naught RMS? It will be Vm by 2 into root of pi, in bracket as usual pi minus alpha plus sine of 2 times of alpha by 2 whole power 1 by 2. This is the expression for output RMS voltage. Then next most important formula is circuit turn off time will be turned to pi by omega c. Initially at this point I kept 2 pi minus beta when I was not considering the effect of freewheeling diode. If I will consider the same circuit but with the freewheeling diode, then this portion will be expressed by pi by omega. Almost if you observe, all these properties will be simply resembling the characteristics of R load. Yes, that is correct. That is the beauty of freewheeling diode. So, connecting the freewheeling diode will be giving some advantages. If you connect freewheeling diode across the load, that is in parallel with the load, what are all the advantages that we will be observing just because of the connection of this freewheeling diode? So there are so many advantages. If you observe, the first one I can say, what will happen is if you connect the freewheeling diode, it will remove all negative spikes. I know many of you remember these things. I am just recapturing once. remove all negative spikes in the output voltage. Output voltage la vara negative portion இது complete என்ன பண்ணிடும், it will be removed. So it will be removing all negative spikes in the output voltage. அப்போ positive voltage மட்டும்தான் வரும். Such that what will happen is the value of V0 average will be increasing. It will be increasing the value of V0 average. Next thing is, because of that, power factor offered by the circuit will be improved. Okay, sir. Next, if you observe the value of the current waveform, if you observe the waveform of the current waveform also will be improved. Current waveform also will be improved. Okay, sir. So when output voltage will be increasing, automatically what will happen? Efficiency of the overall system will be, that is, we can say efficiency of the converter, thyristor efficiency will be increased. So these are all the some of the advantage of connecting the freewheeling diode with our circuit. Do remember these things, it will be helpful for you. Okay, don't forget. Okay, sir. Now it's time to learn about RE load. So let us take the same circuit and I am connecting R. This time we will be connecting E, that is battery. RE load. Let us connect single phase rectifier here. Okay, sir. Many of you guys are confusing here. Exam la வந்து என்ன பண்ணிருப்பாங்க அப்படினா sometimes வந்து DC machine load அப்படின்ட்டு வந்து அவுட்புட்ல கொடுப்பாங்க. நீங்க டைரக்டா என்ன பண்ணிருக்கீங்கன்னா, நம்ம DC மெஷினுக்கு வந்து ஈக்குவலன்ட் சர்க்யூட் வந்து எப்படி வரைஞ்சிருப்போம் அப்படின்னா, பேட்டரி வந்து உள்ள வந்து EMF E, அதுக்கப்புறம் இதுல வந்து என்ன பண்ணிருப்போம் அப்படின்னா ஒன்லி ரெசிஸ்டர் R கன்சிடர் பண்ணிருப்போம். But basically அங்க நம்ம DC மெஷின்ல அனாலிசிஸ் பண்ணும்போது we are not considering the effect of inductance, but it doesn't mean that that inductance is not there. That is wrong. You have to observe one more thing. DC machine load means the effect of inductance will be there. அங்க மெஷின் வந்து only in steady stateல ரன் ஆயிட்டு இருக்கும். அதனால வந்து இந்த காயிலோட எஃபெக்ட் வந்து நம்ம எங்கேயுமே அப்சர்வ் பண்ண மாட்டோம். பட் this is the person who is producing the what armature flux. அங்க armature reaction அப்படிங்கிற ஒரு இம்பார்ட்டன்ட் டேர்ம் வந்து நீங்க DC மெஷின்ல படிப்பீங்க. armature reaction அப்படின்னா என்ன? Interaction between armature flux and main field flux. So the armature flux is responsible வந்து armature இருக்க inductive coil, field coil. So this inductance is very important. DC machine load அப்படின்னு கொடுத்தாங்கன்னா R L E, இதுதான் வந்து DC machine load, not this one. Okay, so try to remember these things in your examination. DC machine data நீங்க இதை வரைஞ்சிருங்க, that is wrong. Okay, sir. So suppose if we connect RE load, then what will happen? RE load la connect பண்ணும்போது என்ன பண்றீங்கன்னா, it is not advisable to calculate the value of V0 average directly. First நீங்க என்ன calculate பண்ணிடுறீங்கன்னா, try to calculate the I0 average. I0 average calculate பண்ணீங்கன்னா, you'll be coming up with the Vm sin omega t minus battery voltage whole divided by resistor R. This can be your I0 average. இதுக்கப்புறம் நீங்க இதை வச்சு என்ன பண்ணிக்கலாம் அப்படின்னா, you know how to calculate the V0 average from I0 average. அதை சப்ஸ்டிட்யூட் பண்ணி நீங்க என்ன பண்ணிக்கலாம், you can explore the output expression for V0 average. That is basically we will be following. அடுத்ததா in these cases இப்போ நம்ம என்ன பண்ணிருப்போம் அப்படின்னா, maximum வந்து firing angle வந்து எவ்வளவு வரும்? So when we are connecting RE load, what is the maximum expected firing angle? Maximum firing angle, I will be giving answer for minimum also. Maximum எவ்வளவு firing angle நம்ம கொடுக்கலாம் அப்படின்றத, that is called theta 2. theta 2 will be, நம்ம இதை பத்தி பேசியிருப்போம். theta 1 னா என்ன, theta 2 னா என்ன லெக்சர்ல பேசியிருப்போம். theta 1 அப்படிங்கிறது என்ன அப்படின்னா, அவுட்புட்ல இருக்க DC சப்ளையோட வேல்யூவும் இன்புட்ல இருந்து சைனசாய்டல் போயிட்டு இல்லையா, அவங்க ரெண்டு பேரும் ரைஸ் ஆகிறப்போ மீட் பண்ற பாயிண்ட் இதான் theta 1. திரும்பவும் அந்த சைனசாய்டல் மேக்ஸிமம் வோல்டேஜ் பாசிட்டிவ்ல ரீச் பண்ணிட்டு திரும்பவும் அது நெகட்டிவ் ஐ மீன் டிக்ரீஸ் ஆகும்போது once again battery ஒரு பாயிண்ட் ரீச் பண்ணும். That is called theta 2. So இவங்க தான் வந்து basically they will decide the initial minimum firing angle and maximum firing angle. So this is the formula to estimate the maximum firing angle. Suppose in your examination if they are asking minimum firing angle, then that will be simply theta 1. இது எப்படி நீங்க கால்குலேட் பண்ணுவீங்க? See, theta 1 formula, it will be simply sin inverse of V max by E. That's all. Sorry, it will be E by V max. I forget. Because we know Vm sin theta 1 will be equal to E. Yes or no? இந்த இடத்துல என்ன பண்ணிருப்போம் அப்படின்னா ஒமேகா t க்கு பதிலா theta 1 replace பண்ணிருப்போம். When omega t will become equal to theta 1, theta 1 க்கு ஈக்குவலா வரும்போது என்ன ஆகும்? Sinusoidal voltage will be equal to E. So just we are equating and we are trying to estimate the value of theta 1. Okay, I hope you all remember these things in future. So basically firing angle வந்து இதுல வந்து lies between what? theta 1 க்கும் theta 2 க்கும் நடுவுல தான் firing angle ஓட range இருக்கும். So example வந்து என்ன கேட்பாங்க அப்படின்னா they will be giving RE load இந்த மாதிரி RLE load வந்து கொடுத்துட்டு you will be requested to find the range of firing angle. Simple அப்படி சொல்றாங்க. Find the range of firing angle. At that time it is very important to remember this point. If you don't remember this, it is too difficult to explore the value, but it is very easy. Okay, fine sir. Similarly, how will you calculate the conduction angle of the thyristor? Gamma, we know, right? Conduction angle of the thyristor வந்து theta 1 minus alpha. Alpha நீங்க calculate பண்ணிடலாம். எப்போ வந்து இது turn on ஆகுதுன்னு சொல்லிட்டு we know how to calculate the theta 1. Just now we saw theta 1 equal to sine inverse of battery voltage divided by the value of maximum input voltage. So from this we can easily estimate the value of conduction angle of the thyristor. So it will be 1 minute. Here it should not be theta 1. It should be, wait guys, conduction angle na theta 2 வந்து yes it should be theta 2. conduction angle தான கேட்டிருக்காங்க. alpha ல இருந்து theta 2 வரைக்கும் தான் diode will be in conduction. So theta 1 உங்களுக்கு எப்படி calculate பண்றதுன்னு தெரியும், right? And you also know theta 1 calculate பண்ணிட்டு then explore the value of theta 2, that is pi minus 180 degree minus theta 1. Then substitute that value here. That's all. Don't think too much. You'll be coming up with the answer. Next, most important parameter is circuit turn off time. How will you explore this value? Phi plus 2 times of theta 1, most important formula, by omega. Many of you guys are not remembering this. Now it is time to keep all those things in your mind. So when we are connecting RE load with a single phase of a rectifier, that is with the thyristor and AC supply, what is the expected circuit turn off time? This is the formula, most important. You know how to explore the value of theta 1? Just to calculate the value of theta 1, substitute here, you will be coming up with this answer. Okay sir. Next, இதில் வந்து என்ன கேட்பாங்க அப்படின்னா one important question. This is IES question actually. The thyristor வந்து இந்த மாதிரி லோட்ல கனெக்ட் ஆயிருக்கும் போது when the moment கேட் வந்து நம்ம என்ன பண்ணுவோம் அப்படின்னா usually we will be giving pulse. பல்ஸை கொடுக்காம கரண்ட் வந்து கண்டினியூஸா நம்ம இன்ஜெக்ட் பண்ணிட்டோம் அப்படின்னா what is the difference? Continuous அப்படின்னா current will be going like this. pulse அப்படின்னா மீனிங் என்ன? கொஞ்ச நேரம் பாஸ் பண்ணுவாங்க then make it 0, again கொஞ்ச நேரம் பாஸ் பண்ணுவாங்க make it 0. இதை ரிமூவ் பண்ணிட்டு இந்த மாதிரி ஒரு பிஹேவியர் வந்து நம்ம கொடுத்தோம் அப்படின்னா then what will happen? See, when the moment your gate current will be continuous நீங்க gate current கொடுத்துட்டே இருந்தீங்க அப்படின்னா then the behavior property SCR ஓட behavior வந்து என்ன ஆகும் அப்படின்னா it will be simply started behaving like a diode. Why? Because நீங்க gate current continuously கொடுக்க ஆரம்பிச்சிட்டீங்க. It means there will be no any control over the thyristor in terms of gate current. We are not controlling the behavior of the thyristor with the help of gate current, because gate current is not discontinuous or it is not being controlled by anyone. So firing angle alpha automatically will become 0 when it will be continuous. When alpha will become 0, thyristor will be converted into diode, one of the IES question. Okay, just to remember this. That's all. So now, it is time to explore the next load. Suppose I am taking the same thyristor, but now we are connecting with the RLE load. Okay, when we are connecting RLE load with the thyristor, then what can be the expected value? As usual, நீங்க என்ன பண்றீங்க அப்படின்னா இந்த மாதிரி load வரும்போது first try to explore the value of I0 average. That will be good for us. இதெல்லாம் வந்து கேட்க மாட்டாங்க, I'm frankly telling, but we can't give assurity. Sometimes வந்து டைரக்டா ஃபார்முலா மட்டும் கேட்கறதுக்கு வாய்ப்பு இருக்கு இல்லையா? இது வரைக்கும் கேட்கலாம். 2 pi r into, so this formula will become, let me write, so V max into cos alpha minus cos beta minus E into alpha, sorry, it should not be, இங்க plus வந்தா இங்க 1 minute guys. Yeah, you can keep plus here, alpha minus beta. That's all. and it should be under. No, we are calculating only average current. That's all. This is the formula to calculate the value of I naught average. Next, from this you can explore the value of V naught average. You know how to do that. V naught average equal to, simply according to Ohm's law, you can go further. Okay, sir. Next, இந்த இடத்துல என்ன கேட்பாங்க அப்படின்னா the maximum reverse voltage across the thyristor RLE load ல வந்து the most important question. Maximum reverse voltage thyristor ல வந்து maximum peak inverse voltage வந்து இங்க எவ்வளவு வரும் அப்படின்னு கேட்பாங்க. It is specific for RLE load. In this case என்ன வரும் அப்படின்னா ரெண்டு பேருமே polarity சேர்ந்து add ஆயிட்டு VM plus E ஓட வேல்யூ வந்து அவுட்புட்ல, that is thyristor வந்து drop ஆகும். So maximum voltage that can be blacked by the thyristor is Vmax plus E, most important term. Next, it is time to explore the value of circuit turn off time. That will be very easy, as usual, 2 pi minus beta by omega. No changes. Okay, fine, sir. Next, sometimes you will be requested to calculate the power factor. That is input power factor only. How will you do that one? That is very simple. I naught வந்து first resistor இருக்கும். ரெசிஸ்டருக்கு நீங்க என்ன பண்ணணும் அப்படின்னா அதுல எவ்வளவு பவர் வந்து டிசிபேட் ஆகுது அப்படிங்கறத கால்குலேட் பண்ணணும். For that you have to use the output RMS current. டைரக்டா அவுட்புட்ல கொடுத்துருவாங்க. பேட்டரியோட வோல்டேஜ் வந்து நீங்க கால்குலேட் பண்ணும்போது you must use average value of the output current. Sir, these both are not same. That's why I am giving the formula. Try to remember it. Then source voltage. இங்க input RMS current, output RMS current same தான், நீங்க டைரக்டா சப்ஸ்டிட் பண்ணிக்கலாம். Remember, when the moment you are trying to calculate the power dissipated across the resistor, this is dissipated power across the resistor. For that you must use output RMS current. It will be directly given in your examination. Whereas to calculate the average power, you must calculate the value of I naught average. You know the formula, just now I have defined. After calculating these two, substitute here in order to know the value of power factor offered by the circuit. Okay, fine, sir. Now, so these are the some of the important things that you must keep it in your mind. அடுத்தது நான் என்ன சொன்னேன், when the value of inductor is very large, example என்ன கொடுப்பாங்கன்னா key கொடுப்பாங்க, inductor is very large அந்த மாதிரி மென்ஷன் பண்றாங்க. வெரி லார்ஜ்னு மென்ஷன் பண்ணாங்களே மீனிங் என்ன அப்படின்னா அவுட்புட்ல கண்டக்ஷன் வந்து எப்படி இருக்கா, கண்டினியூஸ் கண்டக்ஷன் அர்த்தம். இன்டைரக்டா மென்ஷன் பண்ணுவாங்க. கண்டினியூஸ் கண்டக்ஷன் வரும்போது நீங்க ஜெனரலைஸ்டு ஃபார்முலா, நம்ம இனிஷியலா ஒரு டேபுலர் காலம் போட்டோம் இல்லையா டயோடுக்கு, அதே மாதிரி ஜெனரலைஸ்டு ஃபார்முலா வந்து நீங்க சப்ஸ்டிட் பண்ணி யூஸ் பண்ணிக்கலாம். Okay, fine, sir. This is all about half wave rectifier. Let us keep our attention with the full wave rectifier. First நம்ம என்ன பண்ண போறோம் அப்படின்னா we will be taking midpoint. எல்லாத்துக்கும் நான் டிஃபைன் பண்ண முடியாது, ஒரு இதுக்கு மட்டும் ஒரு சில இதுக்கு மட்டும் நான் டிஃபைன் பண்றேன். See, otherwise let me do one thing. Both will be same almost except peak inverse voltage. So you will be either you can take midpoint conversion, midpoint connection or bridge connection, whatever it is. ஏன்னா உங்களுக்கு அவுட்புட்ல வந்து எந்த சேஞ்சஸும் வராது. If you connect, இதுல வந்து என்னன்னா midpoint பொறுத்த வரைக்கும் basically full wave rectifier பொறுத்த வரைக்கும் basically in the examination 95% of the question வந்து directly coming from continuous conduction. Sometimes questions will also be there in discontinuous conduction. Conduction வந்து continuous அப்படின்னு மென்ஷன் பண்ணிட்டு இருந்தாங்கன்னா like how will be indicated with the help of large value of the inductance. இந்த மாதிரி கொடுத்துட்டாங்க அப்படின்னா what you can do is simply for the full wave rectifier, irrespective of the nature of the load, whether you are connecting R load, RL load, RLE load, whatever it is, you can directly write the general formula வந்து என்ன பண்ணிக்கலாம்னா 2 Vm by pi cos alpha நீங்க டைரக்டா எழுதிக்கலாம். So the general formula is 2 Vm by pi cos alpha, generalized formula for all type of load. They won't give a what type of load that they are using. Okay, sir. Suppose this is for continuous conduction. Okay, I will be writing all other things. Similarly, how do I write the RMS voltage? RMS voltage என்ன வரும் அப்படின்னா Vm by root 2. Okay, sir. Then circuit turn off time TC. இதுக்கு என்ன வரும் அப்படின்னா pi minus alpha by omega. Same formula you can observe for continuous conduction RL load. இப்போ நம்ம ஒரு induct R plus L எடுத்துக்கிட்டு full rectifier circuit plus sinusoidal நீங்க observe பண்ணீங்க அப்படின்னா when the value of inductance is very large, this formula is applicable for RL load. Same formula you can produce it. Okay, sir. Suppose now let me specifically define. I am taking RL load. Sir, general formula I have defined and it is also common for applicable for RL load. Okay, this is formula I am talking about. Fine, it is over. Now RL load continuous conduction you can take this formula. At the same time, full wave rectifier continuous conduction கொடுத்தாலே V naught average க்கு formula இதுதான் 2Vmi by cos alpha தான். Okay, fine sir. So அப்ப நம்ம என்ன பண்ணிரோம், let us take RL load. RL load ல when the value of inductance is very large, then you can take this all other parameter. If it is in discontinuous conduction, if the conduction is discontinuous, then what can be the expected formula? Then V naught average can be written as Vm by pi into cos of alpha minus cos of beta. Okay sir. And you can also write inga adutha enna question kepanga appadina power factor. Power factor as usual you can write input power factor formula. It is very important here. Current will get cancelled. You can simply find the output RMS voltage and input RMS voltage. Output RMS voltage substitute panina, you will be getting the answer. Now what is the formula to explore the circuit turn-up time? Most important formula 2 pi minus beta by omega. Just observe the difference. RL load continuous conduction and pi minus alpha by omega. Discontinuous conduction 2 pi minus beta by omega. There is a difference between these two. It is must be observed by you people. Here the most important adutha enna load neenga observe pannotina RLE load. Repeated questions. So RLE load வந்து observe பண்ணீங்க அப்படின்னா as usual, if you take over V naught average, first let us consider continuous conduction. So அப்போ V naught average க்கு என்ன formula வரும்? As usual 2Vm by pi cos alpha. There is no change in this value. Suppose இதில் output RMS voltage கேட்டாங்க அப்படின்னா V naught RMS கேட்டாங்கன்னா simply it will be equal to input RMS voltage. அப்படியே நீங்க எடுத்து substitute பண்ணிக்கலாம். Circuit turn off time Tc, as usual, same formula pi minus alpha by omega. I told now this is common. Here also, if you observe, I wrote the same formula. That's why I told that this is general. Circuit turn off time. And that formula is also applicable for RL load and RLE load. Okay, sir. Now, if you keep your attention with the discontinuous conduction. In case of discontinuous conduction, you must remember one thing, circuit turn off time. That is 2 pi plus theta 1 minus beta by omega. Guys, I am giving the things which are very important in the examination point of view. Question edukra area edadanu enak theriyum, so I am just focusing on it. Some portions on the I may left that you have to recapture it by yourself. You'll have V naught average calculate pandrathu, I naught average. That things can be done by you. Okay, so don't expect everything from my side itself. That's not good. Fine sir. Next it's time to explore. இது வரைக்கும் நம்ம first என்ன பார்த்தோம், just first I took diode மட்டும் எடுத்துக்கிட்டு அதனால என்னென்ன changes வருதுன்னு பார்த்தோம். Next I took thyristor என்ன changes வருதுன்னு பார்த்தோம். Now it is time to combine these two. Suppose ஏதாச்சும் ஒரு சர்க்யூட் வந்து நம்ம diode plus thyristor வச்சு நம்ம manufacture பண்றோம் அப்படின்னா, when your circuit will be having the combination diode plus thyristor ரெண்டுமே சேர்ந்து வருது அப்படின்னா, that is called semi converters. You might be read this term. Semi-converter means that circuit has been manufactured with the help of both diode as well as what? Thyristors. Thyristor is fully controlled, diode is uncontrolled. When we combine these two, it will become semi-controlled. That is called semi-converter. Half partially we can control. That is one half can be controlled, another half cannot be controlled. Consider it is called semi-controlled. That is called single phase semi-converters. So I am talking about single phase only still. So we will be dealing with the single phase semi-converters. Now, single phase semi-converters as usual full bridge rectifier. There will be no doubts. We are going to talk about full wave rectifier. You can consider full wave rectifier, single phase semi-converters. Full wave rectifier means in the output side we will be receiving 2 pulse. That is, output frequency will be equal to 2 times of input frequency. You know that. இதை நம்ம எடுத்துக்கும் போது, so semi-converters வந்து நீங்க எடுத்துக்கும் போது, so one minute guys. Okay. Now, what is the V naught average formula? Most important. This is very, very important. You have to remember Vm by pi into 1 plus cos alpha. That is the formula to explore this value. Similarly, இதில் V naught RMS வந்து sometimes கேட்பாங்க. Just remember this. V naught RMS will become Vm by root 2 into pi C. You 1 minute, I think, in this. Yes, both will come under root only. So you can consider pi minus alpha as usual plus sine 2 alpha by 2 whole power 1 by 2. Okay, sir. Then what is the circuit turn off time? இதில் ஆக்சுவலி என்ன ஒரு ப்ராப்ளம் இருக்கு அப்படின்னா செமி கன்வெர்டர்ஸே இருந்தாலும் சம்டைம்ஸ் என்ன பண்ணுவாங்கன்னா ஃப்ரீவீலிங் டயோட் வந்து கனெக்ட் பண்ணுவாங்க. ஸோ வாட் வி வில் டூ இஸ் லெட் மீ ரைட் வித் ஃப்ரீவீலிங் டயோட் வாட் இஸ் தி சர்க்யூட் டர்ன் ஆஃப் டைம், without freewheeling diode what is the formula to calculate the circuit turn off time. First, with the freewheeling diode the formula to explore the value of circuit turn off time is pi by omega. If you consider without freewheeling diode the circuit turn off time can be expressed pi minus alpha by omega. Now this is the most important formula when we are considering semi converters, and of course V naught average also most repeated area. Question will be often repeated here. Another time this is for continuous conduction, right? I wrote semi converter, and here you can consider this is for continuous conduction, this formula. Suppose if the conduction is not continuous, if you are having discontinuous conduction, then what is the formula to estimate the value of V naught average? Sometimes you will be asked. So what you can do is, this is 1 by pi into Vm into 1 plus cos alpha. The another of is E into, I think it will be pi plus alpha minus beta. Yes, I hope I am correct. This is the formula to explore the value of V naught average when your conduction is discontinuous. I hope you all have understood this. Fine, sir. Now if you take the same thyristor rectifier, 3-phase half controlled, let us take the 3-phase. Let us keep our attention at the 3-phase. In 3-phase, once again we will be covering half-wave rectifier. That is 3-pulse converter. Yes, sir. So the first important thing is we need to talk about firing angle. Firing angle decide based on the value of the firing angle only questions will be asked in the examination. First, sometimes they will define the value of alpha is less than or equal to 30 degree. Another one is alpha is greater than 30 degree firing angle. But alpha firing angle value வந்து 30 degree வந்து கம்மியா இருந்தது இல்ல அதுக்கு ஈக்குவலா இருந்தது அப்படினா its correspondent conduction is called continuous conduction. அப்ப எக்ஸாம்ல வந்து sometimes என்ன கொடுப்பாங்கன்னா the value of alpha is equal to 30 or less than 30 கொடுப்பாங்க. Sometimes they will be calling the circuit is having continuous conduction. Our continuous conduction குள்ள வருது அப்படினா by default you can write that the value of alpha is less than 30. நீங்களாவே கரெக்ட்டா predict பண்ணிக்கணும். When the value of alpha goes beyond 30 degree, automatically conduction will become discontinuous. Do remember this, very important. 3-phase half-wave rectifier நாலே first உங்க மைண்ட்ல வர வேண்டிய term இதுதான். இப்போ இதுல one more thing வந்து என்ன அப்படினா when we are considering இப்போ நம்ம வந்து RL லோட வந்து டைரக்ட்டா அவுட்புட்ல கன்சிடர் பண்றோம் அப்படினா there is no concept of continuous and discontinuous. It doesn't matter whether the value of alpha is less than or equal to 30 degree or the value of alpha is greater than 30 degree. We are using only இதுல வந்து என்ன இருக்கு அப்படினா output average formula வந்து simply only one formula. It will be common for all. We can simply write 3 times of maximum line voltage divided by pi into cosine of alpha. That's a standard fixed formula for all range of alpha. அப்ப இந்த ஆல்பாவோட வேல்யூ less than 30 greater than 30 எல்லாம் யாருக்கு சார் நம்ம கன்சிடர் பண்ண போறோம் அப்படின்னு கேட்டீங்கன்னா it is for R load. When you will be dealing with the R load, these things will be happen. So அப்ப நம்ம R load மட்டும் கன்சிடர் பண்றீங்க அப்படின்னா என்ன வரும் அப்படின்னா first when the value of alpha is less than or equal to 30 degree, first case. இதுல என்ன வரும்னு பாத்தீங்கன்னா the value of V naught average can be simply written as 3 times of maximum line voltage divided by pi into cos alpha. If the value of alpha goes greater than 30 degree, then we can say the value of V naught average will be equal to, we can write V maximum line voltage under bracket it will be 1 by 6 plus root 3 upon 8 pi. Guys, 1 minute. I'm writing the expression for RMS voltage. See, my mind is sometimes annoyingly confusing. Forgive me. That's why we need to keep continuous touch with these subjects. That is RMS voltage for less than 30 degree. Let me write. So V naught average formula for R load only. Specifically, I told you RL load இருந்தா ஒரே formula தான் நான் ஏற்கனவே எழுதிட்டேன். R load தான் when the value of alpha greater than 30 degree, then it will become 3 times of that to root 3 times of maximum line voltage divided by 2 pi. In bracket, it can be written as 1 plus cosine of alpha plus pi by 6. Alpha plus pi by 6. This is the formula. Okay, alpha plus pi by 6. So this is the V naught average formula for this half-wave rectifier 3-phase. Okay, so what you have observed here, so the variation what we observed is that formula V naught average VRMS. நமக்கு என்ன RL load இருந்துச்சுன்னா V naught average will be differ in both cases. But நம்ம RL load எடுத்துக்கிட்டோம் அப்படின்னா எல்லா கேஸ்லயுமே ஒரே வேல்யூ தான். ஆல்பா greater than 30, ஆல்பா less than 30, இந்த மாதிரி எந்த கேசஸுமே RL loadக்கு கிடையாது. Okay, okay sir, fine. Okay, now let us consider the full wave rectifier. So we have been discussed about half wave rectifier, right? Let us keep our attention with the full wave rectifier. So here basically நம்ம இங்க resolve பண்றது வந்து பாத்தீங்கன்னா full waveல 6 pulse மட்டும்தான். So we no need to be bothered about 12 pulse. So I'm only focusing on 6 pulse only. இப்போ 6 pulseல once again நான் என்ன சொன்னேன், it doesn't matter, நம்ம 3 phaseல வந்துட்டாலே alpha ஓட வேல்யூ தான் first வரணும். Half wave என்ன பார்த்தோம், less than 30, less than or equal to 30, greater than 30 பார்த்தோமா. Similarly, if you consider the full wave rectifier, here we must keep it is less than or equal to 60 degree or it is greater than 60 degree. இங்க நம்ம வந்து 60 degree எடுத்துப்போம். In case of half wave it is 30 degree. Fine sir. Now once again R load க்கு தான் இந்த difference வரும். RL load க்கு ஒரே formula தான். If you take R load as usual, when the value of alpha is less than or equal to 60 degree R load, then what is the expected formula for V naught average? Most important. What is the formula? 3 times of VML by pi into cos alpha. Undoubtedly we can write. Okay sir. When the value of alpha, இதில் இன்னொரு formula கேட்பாங்க, V naught RMS உங்களுக்கு calculate பண்ண சொல்லுவாங்க. Let me write that one also. It will be 3 by 2 pi. We should keep all this under root. Then you can consider maximum line voltage, and it will be pi by 3 plus root 3 by 2 into cosine of 2 times of alpha whole power 1 by 2. Yes, this is the formula. This is V naught RMS voltage. Okay sir, fine. When the value of alpha goes less than 60 degree, greater than 60 degree போச்சு அப்படின்னா, what can be the expected V naught average formula? So V naught average can be written as 3 times of maximum line voltage by pi in bracket 1 plus cosine of alpha plus pi by 3. அந்த இடத்துல pi by 6 போட்டிருப்போம் இல்லையா? Here it is pi by 3. Alpha plus pi by 3. So this is the formula to calculate the value of V naught average. Okay sir. Now this is all about full wave rectifier. So in full wave rectifier நீங்க வந்து consider பண்ணீங்க அப்படின்னா, as usual here also we will be having semi converters, there is no doubt. But semi converters ஓட beauty என்ன அப்படின்னா, let me break this one minute guys. Yes, the semi converters ஓட beauty என்ன அப்படின்னா, here also we will be talking about semiconductor na, it will be the combination of diode plus thyristor. That is called a semiconductor. Sometimes இதுக்கு நேம் வந்து என்ன சொல்லுவாங்க அப்படின்னா off controlled rectifier னு சொல்லுவாங்க. ஏன் நான் இது உங்ககிட்ட சொன்னேன்ல, இது வந்து controlled, இது வந்து uncontrolled. அப்ப என்ன டோட்டல்ல ஒரு ஆஃப் மட்டும் தான் கண்ட்ரோல் இருக்கு, இன்னொரு ஆஃப் வந்து uncontrolled இருக்கு. So it is also called off controlled rectifier. Don't forget. Semiconductor is also called off controlled rectifier. இதுல alpha ஓட வேல்யூ வந்து நீங்க less than 60 degree போட்டீங்க அப்படின்னா, it will be equal to full wave rectifier. இதோட ப்ராப்பர்ட்டி வந்து simply equality யாருக்கு ஈக்குவலா இருக்கும், full wave rectifier க்கு. அப்ப நீங்க ஃபார்முலா என்ன எழுதிக்கலாம், V naught average equal to 3 VML by pi into cos alpha. That's all. When the value of alpha greater than or equal to 60 degree, then it will be reflecting the properties of half-wave rectifier. அப்போ V0 averaging formula என்ன வரும்னு பார்த்தீங்கன்னா as usual 3 VML by 2 pi into cos alpha. That's all. Okay, so this is how we are defining the average formulas for rectifier circuits. Okay, I hope you all will be understanding this. So that is how we are defining these formulas. 1 minute, let me cross check this. If you put alpha less than 60 degree, I will be coming up with there are 1 plus also will be coming. 1 minute guys, so it will be less than 60 means இதை கரெக்ட் பண்ணுங்க. When the value of alpha is, sorry guys, it's a gap, ரொம்ப நாள் ஆயிடுச்சு, that's why. So V0 average வந்து alpha வேல்யூக்கு வந்து நம்ம 60 degree less than போட்டிங்க அப்படின்னா, so it will be coming up with 3 VML by 2 pi into 1 plus cos alpha. Yes, this is correct one, you can standardly follow it. When the value of alpha goes greater than or equal to 60 degree, then V0 average formula will become V0 average and PRMS value. Here also I am getting 3 VML by 2 pi into 1 plus cos alpha. See, when we are going from in full wave rectifier, just note பண்ணிக்கோங்க, I don't think 2 will come here. Light confuse it. Just remember this formula, don't put 2 here. And here this is alpha greater than or equal to 60 degree. Just to remember this, I will be cross checking once. Okay, see, just you can keep it in your mind. I don't think that questions will be taken from here, but sometimes questions will be taken in some IAS question gate. You can expect the question from this area. So here I have covered all the formulas that are required in your examination point of view. So it is also very important. நான் இங்க எழுதுறது எல்லாத்தையும் அப்படியே பிளைண்டா வந்து ஃபாலோ பண்ணாதீங்க. My thing is, நான் எழுதும்போது மேபி அன்கான்ஷியஸ்ல என்ன ஆகும் அப்படின்னா 1 or 2 terms மேபி அதுக்கு நம்ம ஷார்ட் நோட்ஸ் இருக்கு இல்லையா, அதை வந்து கம்பேர் பண்ணிக்கோங்க. Mostly I won't do mistake, but unconsciously it will happen sometimes. So கொஞ்சம் கான்ஷியஸாக இருங்க. நீங்கள் ப்ராப்ளம் சால்வ் பண்ணும்போதோ இல்லை எழுதும் போதோ கரெக்டாக இருக்கா, சார் நடத்துறது கரெக்டாக, நம்ம எல்லாத்தையும் கரெக்டாக மேட்ச் பண்ணியிருக்கோமா அப்படிங்கிறத ஒரு டைம் கோ த்ரூ பண்ணிக்கோங்க, ரைட்? So this is all for rectifier circuit. We have completed almost all basics that are required to solve the problem. இதை தாண்டி I know there are so many other things to recapture. In your free time you can revise all those things also, right? Such that while solving the problem just with full confidence, you will be able to solve all the problems. In the next section we will be start solving all numerical questions which are relevant to our rectifier circuits. So this is all for this lecture. Remaining things we will see.